So here we will discuss about the exponential growth model. So we will consider here the growth model in population growth. That means how the population is growing, at what rate. So, and we will try to see how the model is formulated into differential equation, how we can solve it when initial value is given. That means at specific year, something like 2000, 2010, 2002, 2003, something like that, whenever it may be given, wherever. So we will use this in MATLAB and try to see the situations, how we can solve it easily, how we can plot the graph. That means the increase in population according to the year. So we'll see it. Okay, first of all, let us look at the equation. Okay, you see here. So you can see here. This is the exponential growth model. You see, you can go through it. So you can find this in the book as well. So here, you see, this is the rate dx by dt, this is the differential equations, and you can see this dx by dt rx, where r is the growth rate. You can go through it, and x naught is the initial condition, this value of x, that means the population, initial population. So t naught will be given at specific year, and this x naught is the population at time t naught. Okay, so you can also solve this problem analytically, then you will get the solution as xt is equal to x naught e to the power rt, this rate, and t is the time. So let us use MATLAB to solve this. Okay, have here. So what is it? Growth model. So exponential growth model. Growth model. Okay. Let us start here. The code will be like of similar types as you have done in decay, exponential decay model. It will be like almost similar, same conditions and so on. Just the model is different. Thus the difference is just the formulation of the equation, the type of the equation. That's it. So this seems xt. So what is the differential equation? Or d, right? Or d is df. Comma 1 equal to so you see here, in terms of exponential decay model, here it was, the rate was k, so it was, the equation was minus k. So if we put minus here, then if it will become, this growth model will become a what do you call, decay model, the same thing. If you put plus r, that means positive r, so it becomes the growth model, the same thing. So this is the variable r here, so we need the value for r. Okay, suppose the rate is given to be r is equal to this rate will be given to you whenever the question will be given to you, then along the question the rate will be given. So let us take r is equal to 0.017. This is the rate. Okay, so I got this. Okay, so you have written the rate. This is the differential equation. So along with it you need the condition, the initial condition. Okay, so condition is what? X at time 0. That means the initial time 0. Okay, let it be something like 5.3 in billion. Okay, so let us write this up here. 5.3, such that you don't get confused here. 5.3 billion. 5.3 billion. So at let t naught is what you see, 1900 or something like that, 1990. Okay, so this is the condition. T naught is 0, so 1990, starting from 1990. So we will try to calculate the population from 1990. So here we have T naught is 1990. That means we have mentioned here as with 0. So we got this condition. So now we will try to solve this. So you know the method, x solve. What is it? With t. Go to this solve. So OD, and the condition is given as COND. So here it is. You got this. You better write a semicolon here. Okay. This is the solution. So I mentioned. Let us simplify to make it easier to plot. Okay, xt simplify. Set x solve t. So you get this. Okay, so let us try to run this. Okay, so let's name it as growth. One. Okay, growth 1. Sorry, file growth M10. Sorry, you need to put one more equal sign here. Okay, so now let us run it. Okay, so this is the solution. So this is the solution xt. Okay, so this is the solution xt. Now we got the solution. Now we will try to plot using different time. That means at different time, so that you can easily analyze or see the behavior of the graph, how it increases as the time increases. That means the year. So here we have taken t node as 1990, so we will increase it with 5 years, 2 years, 1 year, like 1991, 1992, so it keeps on. So let us take a set of time, so t equal to, starting from 0, okay, the initial one 1990, that means. So first of all, let us increase with 1 year, that means 1990, 1991. So let us take up to 10. Okay, that's it. So take it xt here. You got this. Okay, now let us try to plot. Comma y. So let us run and see. Okay, you see this 5.3 billion, 5.4 billion, it keeps on increasing here. That means 0 is 1990 and 1 is 1991, 1992. It keeps on going, increasing. So according to the year, the population also increases. So now let us check here. Suppose we are increasing with 5, that means 1990, 1995, okay, 2000, and so on. So let us increase it up to, what do you call, 50. Let's see how the graph comes. Okay, you see difference is what, 5, 10, 15, 20. Okay, it keeps on increasing starting from 0 here. Always remember that here 0 is 1990. So you can also change it now. Suppose if you take the initial time something like 2000, okay, 2000, it will not give much more difference. Okay, that means the initial value will be something given to you, 5.3, 5.4, 6 billion, something like that. Okay, so it doesn't matter anything. So here, so this graph, okay, so this is the graph, and yes, the year increases with 5 years starting from 1990, 0 is 1990 here, so 1995, and keeps on increasing, 2000, 2005, 2010, and so on. Okay, so this is the graph. So you can see, or you can predict up to many years. Okay, you can predict it. Take it 100, it will keep on increasing up to 100. So you see from 1990, when you increase up to 10, okay, that means 1990 plus 10, 2000, then definitely you will get the population here at 2000. You will get the population as 10 billion, 20, 15 billion, 20 billion, and so on. It will keep on increasing. So this is the plot. Now you see one more thing. So when you have this analytical solution, as you have done in decay model, so you can also use the analytical solution directly, this analytical solution directly here. Okay, putting x equal to whatever the equation is, then you will not require all these things. Okay, they will not require all these things. So we have done here the usual method using MATLAB to solve the initial value problem. That means ordinary differential equation when the initial condition is given. So no need to go for an analytical solution. Okay, so you can directly solve here. So you got to see the whole picture of the growth model. Okay, as the year goes on increasing and how the population increases. So in the same way, you can predict when you know the rate, growth rate, this R, this is the main thing here. It plays the main role here, the growth rate. If you know the growth rate and the initial that means in the year 2000, if you know the population is something like 10 million, 10 billion, 5 billion, 6 billion, whatever it may be. So if you know the initial value and the rate, then you can predict the population. Okay, like if you know the 2000 value, so you can predict the population of 2020, 2030, okay, 2050, whatever, you get 3000. So this is the whole story of this exponential growth model. So then you have understood it, and you can also see the solution here. You see, this is the solution. Okay, 1990. So this is the 1990. You will get this. Okay, remember that all these values are in billion. Okay, this population, because the condition one is what we're dealing with, billion, 5.3 billion, something like that. So these are all billion. 53 by 10, that means 5.3 billion. At time 0, that means 1990, it is 5.3 billion. So it keeps on increasing at 1995, 2000, okay, increasing with the interval 5. So these are the population at different times. Okay, so you can see this. So you go through it properly. So again, so if you don't understand or if you have any queries, you can ask. Okay, thank you.